Welcome students to the MOOCs course on fuzzy sets, arithmetic and logic. This is lecture number 19. In the last class, I have introduced you to the concept of relations. Given two sets x and y, a relation R x y is defined as a subset of the Cartesian product x cross y, and if A belonging to x is related to B belonging to y, then we represent the relation in the following ways. Through our relation matrix R, where for a crisp set R I j is going to be 1 if the ith element of set X is related to the jth element of set Y, and it is going to be 0 otherwise. Also, we can write it as R say A comma B. Also, we can write it as A R B. So, these are the different notations that you may find in different books or other reading materials. And another fourth way of doing it is through Sagittal diagram. When we extend the concept of relation to fuzzy sets, instead of 0 1, we attach with each pair x I y j number belonging to the interval 0 1, such that the number represents the strength of the relation. This I have explained to you. Let me give you some example. Suppose X is a set comprising of 3 elements A, B, C. Y is a set comprising 4 elements 1, 2, 3, 4, and Z is a set of two elements, let me call them M and P. So, consider the relational matrix R x y. Since x has 3 elements and y has 4 elements, it is going to be a 3 cross 4 matrix, where we have A, B and C, and here we have 4 columns corresponding to 1, 2, 3 and 4. So, we have a 3 cross 4 matrix, and the values will be the strength between the corresponding pair. For example, suppose this matrix is 0.9, 0, 0.7, 0, 0, 0.6, 0, 0.1 and 0, 0, 0, 0.8. This effectively says that, say, A is not related with 2, but the strength of relation between A and 1 is 0.9. Similarly, for all other elements. And then we can have another relation. So, let me call it P y comma z, and let us define it as so there are 4 elements in y. So, these are the 4 elements and there are only 2 elements in z. So, the matrix is going to be 4 cross 2, and suppose the values are 0.2, 0, 0.9, 0.3, 0.4, 0 and 0.5. These are corresponding to M and P. So, this is the matrix that gives us the fuzzy relationship between y and z. Another way of representation is through Sagittal diagram. Say, for example, we have A, B and C. Here we have, say, 1, 2, 3 and 4, and suppose here we have M and P, and between A to 1 it is 0.9, between A to 3 it is 0.7, between B to 2 it is 0.6, between B to 4 it is 0.1, between C to 4 it is 0.8. So, we are not drawing the arrows when the strength of the relationship is 0, because that means that they are not related at all. And now, we draw the relationship between y and z, and that will look like this. between 1 and m it is 0.2, between 2 and m it is 0.9, between 2 and p it is 0.3, between 3 and m it is 0.4, and between 4 and p it is 0.5. So, this gives us the sagittal diagram representing both the relationships R x y and P y z. Given a relationship, we can talk about the inverse. The inverse of a relation R x y is defined as R inverse of y comma x, and the corresponding relation matrix will be R inverse y comma x. Note that the elements R x I comma y j gives the membership value of the relation between x I and y j. Therefore, essentially R x I y j, this element is mu R of x I y j. If we remember this, then we understand that when we talk about R inverse y j x I is the strength of the relation between y j and x I. Therefore, R inverse y j x I is equal to mu R inverse y j comma x I, and therefore, the relation matrix R inverse is actually the transpose of the matrix R. Therefore, with respect to our example R inverse y comma x, this is now going to be a 4 cross 3 matrix, which is going to be 1, 2, 3, 4, and on this side A, B, C, and it is the transpose therefore, it is going to be 0.9, 0, 0.7, 0, 0, 0.6, 0, 0.1 and 0, 0, 0, 0.8. Similarly, P inverse Z y is going to be a 2 cross 4 matrix, and that is going to be point 2, 0, 0.9, 0.3, 0.4, 0 and 0.5. Thus, corresponding to both the relations R and P, we get corresponding inverse relationship. We get corresponding inverse relationship. Given two relations, R x comma y and P y comma z, we can define a new relation Q, suppose, which is defined on x comma z. Question is, what is the relation matrix for Q x z? In Q x z, the value Q x I comma z k, that is the strength of relation between the ith element of set x and the kth element of set z, is defined as maximum over y j belonging to y, minimum of R x I y j comma P y j z k. Since we have R is equal to 0.90, 0.70, 0.6, 0.1, 0, 0, 0.8 and P is equal to 0.2, 0, 0.9, 0.3, 0.4, 0 and 0.5. Therefore, Q x z is equal to R composition with P is equal to, now let us look at the operation. it is minimum over all y are of x, y and y z. So, let us consider the matrix Q. We know that its dimension is going to be 3 cross 2, because there are 3 rows here and there are 2 columns here, and the ijth element will look at the minimum of these pairs. The operation is very similar to matrix multiplication, but there we take the product and add it. Here instead of multiplication we are looking at the minimum, and instead of final addition we are looking at the maximum. So, in this case the element is going to be minimum of 0.9 and 0.2, which is 0.2, minimum of 0 and 0.9, which is going to be 0, minimum of 0.7 and 0.4, which is going to be 0.4, and in this case it is going to be 0. Therefore, the first row first column element is going to be 0.4. For your benefit, let me write this is A, B, C and this is M and P. We are looking at the strength of relationship between the elements of x and elements of z. In a similar way, first row second column is going to be maximum of 0, 0, 0 and 0. Therefore, this is going to be 0. In a similar way, this is maximum of 0, 0.6, 0 and 0. Therefore, this is going to be 0.6. Second row second column 0, 0.3, 0, 0.1. Therefore, this is going to be 0.3 and this is going to be 0 and this is going to be 0.5. Thus, even if the elements of two sets are not directly related, there is an y such that the set x is related to y and set y is related to z. Once those definitions are there, we can get the relationship between x and z. What is the inverse of q is equal to r composed with p? Q inverse is between z and x is going to be the transpose of R P. Therefore, we can write Q inverse of z x is equal to P inverse z y composed with R inverse y x. I illustrate you with respect to the matrix Q. We have already got Q here. So, we from here we can write Q inverse is equal to 0.40, 0.6, 0.3, 0, 0.5, M, N, and these are corresponding to A, B, C. We already had R inverse and P inverse. So, let us first compute P inverse composed with R inverse. And we know it is going to be 2 cross 3. So, this is M, this is N, and the elements here are A, B, C. So, this is going to be maximum of 0.2, 0, 0.40, therefore, 0.4, 0, 0.6, 0, 0, 0.6 and 0, 0, 0, 0, therefore, it is going to be 0. Similarly, for the second row, the minimum is the maximum of 0, 0, 0 and 0, therefore, this is going to be 0, 0, 0.3, 0, 0.1, therefore, this is going to be 0.3 and 0, 0, 0 and 0.5. So, from here we get that the composition of P inverse and R inverse gives us the matrix 0.4, 0.6, 0, 0, 0.3, 0.5, and if we now look at this, you can see that we have got the same matrix here. So, this verifies that Q inverse is equal to P inverse composed with R inverse. In the last class, I have given you two matrices R x y, which is between B, D, E and P, and S, C, L, and the matrix was 0.2, 0.8, 1, 1, 0.9, 0.2, 0.5, 0.9, 0 and 0.2, 0.3, 1, and also a P, Y, Z, and the matrix was S, C, L, F, A, M, and the matrix was 0.3, 1, 0.1, 0.2, 0.9, 0.7 and 0.8, 0.1, 0.3. I suggest that with respect to these two matrices, you verify that Q inverse is equal to P inverse composed with R inverse holds. One possible question can two different relations be associated? For example, if x is related to y through a relation R and y is related to z through a relation P, then how x can be associated with z? One important answer in this regard comes from join operation. So, now I explain join operation. Given two relations R x y and P y z, the join operation creates triplets of the form x I y j z k, and the strength of x I y j, if I call it say j, x I y j and z k is equal to minimum of R x I y j and P y j z k. In order to demonstrate that, let us go back to the sagittal diagram that I have shown some time back. From here we can easily get the join of R x y and P y z. The advantage of sagittal diagram is that we do not draw the arrows with 0 strength. Therefore, it is very clear which are the triplets are related. For example, A 1 m is one possible whose value is going to be minimum of 0.9 and 0.2, that is 0.2. Similarly, another possible relation is A 3 m, and its value is going to be minimum of 0.7 and 0.4, which is going to be 0.4. Keeping that in mind, we now write the J matrix for x I, y j and z k, and that is going to be as follows: A 1 m and the value is going to be 0.2, A 3 m and its value is going to be 0.4, B 2 m and its value is going to be 0.6, B 4 p, before that we have B 2 p, B 2 p, B 4 p and C 4 p. These are the 3 triplets left. For B 2 p, the value is going to be 0.3, B 4 p and this value is 0.1, and finally, C 4 p whose value is going to be 0.5. So, this gives us the join operation between x, y and z. Corresponding to each triplet, we get the corresponding strength. The question is, are composition and join related in some way? Because in composition we are looking at only the x and z, but in join we are looking at all the 3 x, y and z. So, to get the composition, we can use here this joint matrix. So, let me give it the name R composed with P, and we know the values are going to be A, B, C, and here it is M and P. Now, let us look at all those triplets where A is related to M. So, these are the two triplets when A is related to M. So, let us look at the maximum of these two, that is 0.4. So, let us put the value 0.4 against A M. Against B M there is only one triplet. So, its value is 0.6. Between C and M there is nothing. Between A and P there is nothing. Between B and P we have two such triplets. Let us take the max of them, and that is 0.3, and between C and P it is 0.5. So, from the J matrix, by taking the max operation between these triplets, we can get a matrix. We are claiming that it is going to be R composed with P. If we look at, actually we have computed the composition of R and P, and we have got this matrix, and if we compare between these two, we can see that we are getting the same matrix back here. 0.40, 0.6.3, 0.5, 0.40, 0.6.3, 0.5. So, join and composition are not completely independent. We can easily get the join operation from the composition as well. With that background, let us look at a special type of relations, relation between elements of the same set, that is, given a set X, we have a relation R x comma x. We have already seen such an example in our last class, when I was talking about the distance relation between cities of India, and then we have along the columns the set of cities, along the rows then same set of cities, and the ijth element is looking at a measure of the distant property between the cities x I and y j. Like that, many different relations can be defined between the elements of the same set. However, the nature of the relationship is governed by three basic properties. What are these? First one is reflexivity, the second one is symmetricity, and the third one is transitivity. Let me first define these with respect to crisp sets. a relation or between the same set X is said to be reflexive if for all x I belonging to X, x I is related to itself, or R x I comma x I belongs to R. It is said to be irreflexive if there exists some x j belonging to X such that the pair x j does not belong to R. That means, if there exists at least one element such that it is not related to itself, then we call the relationship irreflexive. It is said to be anti-reflexive if for all x I does not belong to R. So, if you look at the definitions carefully, you will understand that for all element x I, if x I is related to x I, then we call it reflexive. If there exists some element for which it is not related to itself, then we call it irreflexive, and if for all the elements that relationship does not hold, then we call it anti-reflexive. Now, let us look at symmetricity. R is said to be symmetric if given x I and x j belonging to R, x I x belonging to X, x I x j belonging to R implies x j x I belonging to R. That means, if x I is related to x j, then x j is also related to x I, and that is for all pairs x I x j. Quite naturally, if a relation is symmetric, then corresponding relation matrix is going to be a symmetric matrix. As before, it is to be called asymmetric if there exists pair x I x j such that x I x j belongs to R, but x j x I does not belong to R. So, if for one pair that does not hold, then we call it asymmetric. A relationship is said to be antisymmetric if xi xj belongs to R and xj xi belongs to R implies xi is equal to xj. It is to be called strictly antisymmetric if xi xj belongs to R implies xj xi does not belong to R. Let us give an example. Consider a set A and let x be all possible subsets of power set of A. Let x and y be two elements of x, that is power set of A, which we denoted as P A. Define R between two pairs x y if x is contained in y. That means, x is a subset of A, y is another subset of A, and we are saying if x is contained or equal to y, then x is related to y. Note, R is reflexive because for any subset of A, let me give it a name, say S, S is contained in itself. R is antisymmetric. R is antisymmetric. Since x is contained in y and y is contained in x implies x is equal to y. However, if we consider x is related to y, if x is strictly contained in y, then we see that x is R is irreflexive, because no set can be strictly contained in itself, and it is strictly antisymmetric, since if x is contained in y, then y is not contained in x. The third property is called transitivity. R is said to be transitive if x is related to y and y is related to z, implies x is related to z. It is called non-transitive if there exist x, y, z such that x, y belongs to R, but and y, z belongs to R, but x, z does not belong to R. So, if there exists any such triplet, then we call it non-transitive, and it is called intransitive if for all triplets x, y, z, x, y belongs to R and y, z belonging to R implies x, z does not belong to R. So, we have got reflexivity. There are three possibilities there. We have seen symmetricity, there are four possibilities, and we have transitivity, there also we have three possibilities. Thus, we can combine the three properties in 3 cross 4 cross 3 possible ways. Depending upon which particular combination we choose, we can define a different type of relation on the same set X. Some such important relations are equivalence relation, which is reflexive, symmetric and transitive. Another one is partially ordered, which is reflexive, antisymmetric and transitive. Okay, students, I stop here today. In the next class, I shall start with equivalence relation, and then also we will show how the crisp relationship can be extended to fuzzy sets by slightly changing the definitions of reflexivity, symmetricity and transitivity. Thank you so much.